the slides?
Yes.
Okay, excellent. Okay, good afternoon, everyone, or morning or evening, depending on where you are. First, I would like to thank the organizers for arranging this meeting and for giving me this opportunity to talk here about our research. We have heard quite a few excellent presentations about applications of parahydrogen in NMR. In my contribution, I would like to talk about parahydrogen-based hyperpolarization in exploring different molecular properties. Specifically, how can the SABRE help us in observing molecular effects known as nuclear magneto-optics? This talk is split into two parts. In the first half, I will introduce what is nuclear magneto-optics, because it might be unfamiliar for some of you, and why we are interested in it and how we measure it. In the second part, we will look at our implementation of a SABRE polarizer that has been specifically designed with features that are required for measurements of these phenomena. So what is a nuclear magneto-optic effect? To start this, let's start with, to answer this question, let's start with classical magneto-optics. Imagine we have a sample of isotropic liquid, for example, pyridine, like is shown here. And through this sample, we shine a rain of linearly polarized light. If the wavelength of the beam is far from absorption band of the molecule, it will pass through the sample practically unchanged, and we would not observe any significant optical effects. However, if we also applied a magnetic field along the direction of the light beam, we would see that the plane of polarization actually rotates a little bit. This effect is known as Faraday optical rotation. It was observed by Michael Faraday, and it is an example of classical magneto-optic effect. That means that it is a change of the state of light caused by magnetic field. This angle of rotation that happens here can be described by three parameters. First, we have a material constant, which is called Verde constant. Then we have the length of the sample through which the beam travels. And then finally, we have the strength of the magnetic field in the direction of the light beam. That also means that if we reverse the direction of the beam, then this angle of rotation now changes the sign as well. So if we now go back to our initial sample of pyridine, and we have again the linearly polarized light going through that. And now instead of applying external magnetic field, we instead manipulate some of the spins in the sample so that we get the magnetization along the light beam. What we know is that if nucleus has a spin, it also possesses a magnetic moment. So that means that we are here effectively creating small magnetic fields inside the sample. And this will also lead to a rotation of the plane of polarization. Since this rotation is caused by the fields from the nuclear spins, it is called nuclear spin-induced optical rotation, or NSOR for short. This effect is dependent on four parameters, or it can be described as being dependent on four parameters. The first one is molar NSOR. It is specific for both the molecule and also the nucleus in particular. Then we have the concentration of the nucleus in the sample. Again, the length of the sample through which the beam travels. And instead of the external magnetic field, we here have the magnitude of the magnetization. So it is related to the polarization. Similarly, as in the case of Faraday rotation, if we reverse the magnetization to be antiparallel with the light beam, this plane of polarization will again switch side to the opposite direction. What is different compared to the Faraday rotation is that this is a nuclear specific effect, which means that if our magnetization originates from protons, let's say in ortho position in pyridine in here, it produces some angle of rotation. But if we were to polarize, for example, protons in the meta position, this angle would be different. So NSOR is a nuclear magneto-optic effect, which we can in general define as a change of the polarization state of light caused by nuclear spins. NSOR was the first of these that was observed and is by far the most studied and most well understood of these. Just a short overview, there is also another one that is called nuclear spin-induced circular dichroism. This one is related to the difference in absorption of circularly polarized components of light and it carries information about the excited states of the molecules. And there are three effects known as Cotton-Mouton-like effects, which have in common that they are quadratic in the magnetic interaction instead of linear, and these magnetic fields are oriented perpendicular to the beam instead of being parallel with it. These effects are related to things like dipolar couplings and quadrupolar couplings. Let's have a closer look at the NSOR shortly. So as we have said, if the magnetization is oriented with respect to the light beam parallel or antiparallel, the plane of polarization rotates in opposite directions. That means that if the magnetization precesses in the plane in which the beam is traveling, the NSOR will be modulated by the Larmor frequency of the nucleus producing the magnetization. This allows us to separate different nuclei in the experiment. In addition, as we noted before, the NSOR intensity changes depending on the chemical environment of the nucleus. This is in contrast to NMR, where, for example, if we take ethanol molecule, one proton from CH3 group will give the same intensity in NMR as one proton from CH2 group. This is not the case in NSOR, where the magnetization from these two protons produces different angles of rotation. And recently, we have actually theoretically shown that this effect is directly related to the molecular structure features. So that means that nuclei in different chemical groups have, in addition to a specific range of Larmor frequencies that we are familiar with, also a range of characteristic NSOR values, which depend on the multiplicity of the nearby bonds, atoms that they are bound to, and the local isomerism. We are trying to measure this angle of rotation, so that is our signal, and we want, of course, to maximize this. We have 4 parameters that we can play with. Well, not really, only 3, because the smaller NSOR is the effect that we are actually measuring. We cannot change that. What we can change is the molar concentration of the nucleus, the length of the sample by, for example, bouncing the beam back and forth several times, or the most importantly, the spin polarization, because this is where we can get several orders of magnitude. We cannot really improve, for example, the molar concentration by orders of magnitude because it is bound by the physical properties of the sample. What is also important to note here is that NSOR experiments often require many repetitions because the signal overall is rather weak, and these long measurement times can be up to tens of minutes. That means that our technique of polarization needs to be repeatable or ideally continuous. And in addition, our cells also have significantly larger volumes than in NMR. So our polarization method should also be able to produce significant volume of sample in a given time period. So just shortly over the instrumentation, this is the sketch of a low field experiment that we can use to measure NSOR. So here we have a sample that sits inside 2 coils that are orthogonal to that produce magnetic fields orthogonal to the incoming light beam. One generates static magnetic field, and one generates the magnetic field that we use to spin lock the magnetization. Here we have the beam that goes through the sample, and after it passes through, it is split into 2 components, horizontal and vertical. Initially, it has 45 degrees, so that means that these 2 components are equal, but as the NSOR flips back and forth because our magnetization changes direction with the beam, these 2 components change intensities, and it can be amplified and converted to NSOR. The magnetization is forced to precess in the XY plane, and we do this using the spin locking field B1. And to distinguish the real signal from electric pickup that we can get from this coil produced in the B1 field, we also modulate the static field between 2 values. In 1/2 of the time, the Larmor frequencies correspond to the spin locking field, so that means that the spin locking is efficient. And in the other half of the time, the B0 field is put to significantly lower values so that the spin locking is not efficient and the magnetization is not spin locked along the light beam in a way that we would observe it. Of course, this is a low field setup with 20 kilohertz, and in such setup, we cannot expect any appreciable thermal polarization. So that means that we usually resort to some external polarization system from which we can get sufficiently polarized sample inside the measurement cell, and then we circulate it back for repolarization. In the simplest case, this can be a permanent magnet, where we literally put a bottle of our sample inside the magnet, and then we have a pump and it continuously circles. Or we can have also some hyperpolarization instrument which would provide us with significantly higher polarization and signal. In our case, we are particularly interested in SABRE for several reasons. First, of course, it is affordable polarization method. Second, SABRE does not change the polarized substrate, so that we can repeat the measurements with the same sample over and over, which is beneficial because we have long measurements. And the repetitions themselves are quite fast and repeatable, and it is also possible to automate them in several ways, as has been shown in literature. This is just a selection of some of the papers. There are many more, as we are all aware of. So let's have a look at the polarizer that actually is capable of producing sufficient volumes of the sample. This is the basic schematic of the polarizer, and I will go through it as I describe how it operates. First, we need to introduce the sample, which we do through this sample valve, and we put it into this glass vessel. And after the sample is inside, we can close the rest of the system and evacuate this blue part, and also use liquid nitrogen to efficiently degas the sample. After we degas the sample, we transfer it to another cell here by applying a slight overpressure of parahydrogen gas. And after the sample is transferred here, we can start the SABRE polarization itself by switching the parahydrogen flow to actually go through this tubing. That initiates bubbling through the sample, and then the excess hydrogen escapes through this back pressure regulator. So that means that we can maintain stable pressure inside the system, while at the same time we also have a constant bubbling of fresh parahydrogen. Finally, we here have a pump that is continuously transferring the sample between the polarizing cell and the measurement system. So as you can see, this is conceptually a very simple instrumentation that relies on basic physical mixing of liquid and gas, but it works quite efficiently. The sample is being continuously pumped here, and the hydrogen itself continuously flows. And once this is set up, it can run on its own without any input for the user for hours. Here are some key performance numbers. We usually operate it at about 5 bars, but we have tested it for up to 7. The sample flow rate can be up to almost 3 cubic centimeters per second, which is, I think, quite high for liquid. The hydrogen flow rates can be up to 1.8 standard cubic centimeters, though there is a significant diminishing of efficiency at high flow rates, so we don't usually go that high. And with our cubing, the linear speed of the transfer of the sample between the polarization cell and the instrument is more than 30 centimeters per second. So within, let's say, a second and a half, the sample can get back and forth. With this instrumentation, we observe more than 100 times enhancement compared to the thermal polarization in 300 megahertz magnet for pyridine. This is an example of how this polarizer performs for NMR. The red line corresponds to thermally polarized sample of pyridine and methanol. And we can see that in this case, the pyridine signals are barely visible here. And it is also worth pointing out that in this case, we have used normal methanol, not the deuterated one, which is why the methanol signals are so large here. When we switch on the polarizer, the flow, and we open the parahydrogen, we can see that the signal of pyridine increases significantly. So we see that we have hyperpolarization. And also notably, at the same time, the signals of the methanol diminish. This is because we are using such a high flow rate that the methanol, which in this case is mainly polarized thermally, just doesn't stay long enough in the magnet to be sufficiently polarized. So this is one of the reasons also why we could in principle use non-deuterated solvents even for signals that would be rather close to it because of this diminishing. We can also use this system for MRI, and here are examples of 3 images of a tubing through which we have the flow of our sample. And these images were taken using soft pulses focusing on either pyridine or methanol signals. On the left, we have the image using thermally polarized pyridine, which produces practically no observable signal. In the middle, we can see quite nice, strong signal of the pyridine, on the other hand, once we switch on the SABRE. And on the right side, we have taken image of methanol for comparison. As we can see, it is weaker overall than in the case of pyridine, which is consistent with what we have seen in NMR. In the lower part of the figure here is the profile of the intensity along the x-axis. And what we see here is a difference in the profile, which can be explained by the different origin of the polarization. So in the case of hyperpolarized pyridine, the polarization is coming from outside, and in the case of methanol, it is being generated inside the magnet. So as we know, the sample that is near the edge of the tubing stays there for the longest time. So the thermal polarization in the case of methanol increases, but the thermal polarization in the case of pyridine actually decreases the signal there. And finally, this is the main result for how this polarizer helps us to improve the measurements of NSOR. Know that, as we have said before, the signal appears at the modulation frequency of the B0 field, which was 1 Hertz. I don't know if I have stressed it enough. So on the left, we have a reference measurement of NSOR in neat pure pyridine. So this is no solution, this is just a pure pyridine, which is a concentration of more than 12 mol per liter. And still we see that the signal is quite weak. This sample was polarized thermally in 600 MHz magnet, which leads to the polarization level of roughly 1.6 times 10 to the power of -5 in the measurement cell. In the sensor, on the other hand, we have NSOR of pyridine that has been hyperpolarized with SABRE. So we have now the concentration that is over 100 times lower than in the previous case. But thanks to SABRE, we can achieve polarization levels of roughly 1/3%, which makes up for this concentration difference. And as far as we know, this is the lowest reported concentration for measurements of these effects to date. And as a direct consequence of this, it also enables us to measure qualitatively new samples such as pyrazine, which in its pure form is solid at normal conditions, which means that it would be very difficult to perform this kind of measurements, because there will be numerous experimental challenges such as continuous polarization and transfer of the sample in a similar way as with liquids. And of course, the light would refract and scatter on the crystals. So this is only possible to measure in solution, and we have constructed this SABRE polarizer that has these two important features for us, which is to have high sample throughput and also continuous operation. With the NSOR, it allows us to lower the measurable concentrations by more than 2 orders of magnitude, and also investigate completely new samples such as solids, which was not possible with the previous instrumentations. So here I would like to thank the people who contributed to the presented work and also my funders for their generous support. And this is the conclusion of my talk, and I will gladly answer any questions.
Thank you. Let's start with the first question. What are the materials used in the flow reactor for the cell and the tubing? Are they glass, metal, plastic?
The containers, the cells, this one and this one are glass, and the rest is it's a standard tubing from Swadelock. I believe it's a PEEK, could be, or yeah, it's some kind of plastic, some kind of chemically inert plastic.
Okay. What is the volume of liquid being polarized in the polarization vessel in the continuous flow setup?
Yes, in this particular setup, the volume is pretty significant, as you can probably imagine, which I think that the lowest we achieved was like 40 milliliters, which, given that we can use non-deuterated solvent, is quite achievable. But we were also thinking that this vessel is in principle unnecessarily wide, so it could probably be cut by at least a third by making the vessel more narrow and perhaps higher. And of course, the tubing presents a lot of that volume, so that also contributes to it.
Next question, is the image taken optically, or could it be Yes, that image. Those images, sorry.
No, these are MRIs.
Okay,
This is just an MRI slice of a tubing.
thank you. Next question. What is the largest NSOR rotation that you have seen?
Well, I wouldn't say that we have achieved like significantly a larger NSOR in absolute values. What we were after was to actually decrease the concentration. So as you can see, we are talking here about nanoradians, which is roughly on the order of magnitude as what other experiments observed as well. So we didn't go for highest intensity, but like the enabling of different kind of experiments in this case. So I think that about these 2 nanoradians is roughly where we are.
What can you learn from NSOR that you cannot learn from NMR?
Well, this is still an open question that we are actively working on. But for example, in this case, you can see that given the position of the nuclei, whether it is at the end of the chain or inside the chain, you can see that you can actually have even a change of sign in NSOR compared to these 2. So if we imagine that we would use a simple 1D NMR experiment on this, these 2 signals would be pretty close together. And in some more complicated situations, it might be difficult to distinguish what is the actual local structure of the molecule around here. But we have seen that if you, as you attach different kind of substituents to it, like if you have terminal group or if you have group that corresponds to quaternary carbons, these values vary quite a bit. So in addition to chemical shift, you also could have kind of an optical resolution in this direction, that one nucleus would give you this signal and the other one would give you signal of opposite value, but they would be still pretty close in chemical shift. So I think that there is a potential for additional contrast.
Can you give some insight into why the effect depends on the location of the nucleus and the molecule? Is there a near-resonant optical transition?
In this case that we have investigated recently, we took care of the fact that there is no near optical resonance, because yes, it is true that if you have nearby optical resonance, that these signals would shoot up significantly. So this is basically done just, this is basically the effect of the local spin orbit coupling operator that is present in this effect.